Thank you. It's nice to be back, and thanks for coming. My topic today is a single question. Does the world embody beautiful ideas? And this is a question that's been asked for a long time, and both the meaning and of the question and the answer have changed over time. So I'll include some history and culture in the discussion. It's a complicated story, but I'm going to vastly oversimplify it by making it a tale of heroes. And I'll personify the various ideas. So the line is that Pythagoras and Plato intuited that that the world should embody beautiful ideas. Newton and Maxwell demonstrated in impressive cases how it could, but it's really only in the 20th century, and especially with the development of quantum physics as the description of the world, that we can answer with a much more resounding yes. And that is the reason for my title, Quantum Beauty. Oops, sorry, slow response. Quantum Beauty, where the description of the real calls forth the ideal. So let me start with Pythagoras. And again, this is not the historical Pythagoras. The historical Pythagoras is a very vague figure. But the important Pythagoras is the Pythagoras that was invented and became very influential over the centuries. Sort of, if there wasn't a Pythagoras, he would have to be invented, and he was. So I'll be discussing this fictitious Pythagoras as if he were real. And we even know what he looked like. This is according to Raphael in the School of Athens. There's Pythagoras. And he's writing something which is a little difficult to read, but I blew it up and studied it carefully, and found that if you translated it, what he's writing is that all things are numbers, his very famous credo. It's difficult to tell exactly at this separation in time and space exactly what he meant by that, but one thing that certainly impressed Pythagoras and colored his view of the world was Pythagoras' theorem. Pythagoras' theorem, of course, famously states a relationship between the different sides of right triangles, that if you compute the areas, which geometrically can be the operation of drawing squares on the different sides and dividing them up into standard squares, and then if you count the standard squares on the different sides, that the sum of the two smaller squares adds up to the larger square. Now, of course, these days that's a very common part of knowledge. People learn it in high school, if not sooner. But if you step back and imagine what something like this meant to Pythagoras, I think it's an astonishing relationship, and one can understand why it had such an impact not only on Pythagoras but subsequent philosophers, because it related something in the concept world, the world of numbers, to something very, very much in the real world, sizes and shapes of things. Pythagoras' other famous invention or discovery was in the field of music and the harmony of sounds, where again he discovered that if you play this monochord instrument, which was the favored musical instrument in ancient Greece, and you have strings under tension, strings of equal length. If the tensions are in ratios of small whole numbers, then the different sounds will sound well together. They're in harmony. Likewise, if you hold the strings down and they are under equal tension, the notes will sound in harmony if and only if the ratio of the lengths are small whole numbers. So if the ratio is 2 to 1, then you have the octave. If it's 3 to 2, then you have the dominant fifth, and so forth. This again is an astonishing mapping of concept world into the physical world. Here, the harmony of sounds, a very physical, sensory thing, is related to something that a priori seems to have absolutely nothing to do with it, the rationality, the governance of the phenomena by small whole numbers. So these were remarkable but isolated observations. They became the basis of, or the inspiration for, a more detailed view of the world, especially in Plato. So let me introduce one of the things that Plato is most famous for. And as with many of the things that Plato is most famous for, he didn't invent it. These are the Platonic solids. If you visit the Ashmolean Museum at Oxford University, they have on display these dice, thought to be involved in an early form of Dungeons and Dragons, and dated from 2000 BC, where each of the Platonic solids is realized as one of the dice. Well, to this audience, I'm a little embarrassed to present this, but, well, let's pretend you're all philosophers. These are the Platonic solids. Let me introduce what they are and what they meant to the people at the time. A simpler concept that we should contrast is the idea of regular polygons. If you ask for planar figures, two-dimensional figures, that have all equal sides and all equal angles, well, you can make an equilateral triangle, you can make a square, you can make a figure that's the inspiration for a building in Washington, you can make stop signs and so forth. You can make you can make a figure like that with any number of sides. Those are the regular polygons. One three-dimensional generalization of that, however, in some sense the most direct one, is to ask for solids, all of whose faces are the same, and if you like, are regular polygons, and all of which have equal angles and meet in similar geometric configurations. And now, instead of an infinite number, you find there are just 5. The tetrahedron, icosahedron, dodecahedron, octahedron, and cube. Those 5 dice. At the time, it was speculated or thought that there were 4 elements: earth, air, fire, and water. And 4 is very close to 5. So Plato constructed a theory based on these solids in the Timaeus, according to which the different elements were associated with atoms or building blocks of these different shapes. And there's even kind of physics that goes with it. That tetrahedron is pointy, it's sharp, so if you get hit by tetrahedra, it kind of stings. That's fire. The icosahedron is close to being smooth, so it flows. That's water. For some reason, the octahedron is air. and earth packs and kind of gets stuck, and we know that's how cubes can be if you have a lot of little cubes. Now 4 is not quite equal to 5, so a lesser thinker than Plato might have been discouraged. But a genius is not deterred, and Plato postulated that the dodecahedron is the shape of the whole universe. Later, Aristotle modified this theory. According to him, the dodecahedron was the substance out of which the celestial ether was composed. So he got 5 equals 5. Now, nowadays we don't accept this theory in detail, but as you'll see, there's a real connection between these ideas and modern ideas. I think that's one of the things I want to get across especially. And here, if you interpret it generously, what he's getting to, what they're getting to, is the idea that a way to find that a possible finite number of structures exist in the world and could be associated with the building blocks of the world that are conceptual is that symmetry could define a limited number of possibilities that you can use as candidates. Okay, so leaping ahead a couple of centuries. The beginning of classical physics, or the culmination of the early part of classical physics, is the work of Newton. One could say quite a bit about the work of Newton, but let me just abstract 2 particularly key points that are close to the theme of this lecture. One major idea that Newton exemplified in extraordinary power is the idea that we now call reductionism, but he called it much more prettily analysis and synthesis. And the basic idea is that to understand something in the physical world, a good strategy can be to break it down into small pieces whose properties are reproducible and can be understood fully. And then once you've analyzed the small bits and how they behave and how they interact with each other, to build back up the description of the more complicated things you encounter in the natural world. The purest example of this was in his analysis of light, where he showed that natural white light, say from the sun, if you put it through a prism and take out just one color, it should be red. This way, I guess, where you block. I'm not sure how this diagram is supposed to be interpreted, but if you take out a particular band from the rainbow cast by a prism, you find a pure light, and then if you deflect that pure light by other prisms, it stays the same color, gets deflected by the same angle. Other colors would be deflected by different angles. And Newton tried many, many ways of changing the color of a light beam once it was pure, and found that he couldn't, so that the pure colors of light were the irreducible building blocks, and then you could crucially build white light back up. It's a little hard to see in the projection, but there's white light over here and here. If you break it up, as in here, let all the colors propagate, then you can bring it back together and get white light of the same kind you started with. This was Newton's strategy also in more abstract realms, in mathematics, to understand the areas of figures, break them down into infinitesimal bits, and then integrate them back up. In mechanics, look at the motions over infinitesimal times, which obey simple laws, and then build them back up. Let me show that at work in its most impressive incarnation, and to me, in the most beautiful figure in all the scientific literature. This is the first figure in Newton's Principia, where what's shown is what happens if you imagine standing on top of a mountain and throwing a rock in a horizontal direction harder and harder. Okay? If you throw it a little bit, we know from everyday experience what will happen. It'll go for a while and fall down. If you throw it a little harder, it goes further, further, further. And just thinking about it, what happens if you throw it really hard, so that it doesn't reach the ground or does until it's come all the way back. Then you have not a falling rock, but an orbit. And so you could also imagine standing on it so it hits you in the back of the head. Then you can also imagine a taller mountain, throwing it from a taller mountain, and have orbits or orbits. I think this is the way, not by watching an apple fall from a tree, this is the way that Newton really discovered that the force of gravity could be universal, that falling is the same as orbiting, or more precisely, that orbiting can be considered as constantly falling, but towards a moving target. This approach and this figure and example showed a radically different view of what the structure of the world is and where beauty in the laws of physics could lie, a larger view. Here, whereas in Plato and Pythagoras it was sizes and shapes of definite things, especially in those Platonic solids, here any particular orbit is nothing special. What makes the beauty of the figure is the underlying concepts and the totality of the dynamical description. By the way, Newton, I'm sure, also asked himself, suppose you threw the rock even harder and calculated what the orbit would look like, found it was an ellipse, and at that point probably recollected that Kepler had said something about ellipses in his laws of planetary motion. So this is what Newton looked like as he was doing all that. According to William Blake, you can see the enormous cultural impression that he made on his contemporaries, and the message that his work conveyed. Besides these technical innovations, was the idea that one should be ambitious to get a precise view of the world, not a rough view in terms of atoms that slither past each other and have more or less the right shape and seem qualitatively okay, but precise mathematical formulas and measurements. Blake continues with this figure, showing that that's the way the world is constructed, or that's the way Newton's triumph leads you to think the world is constructed along conceptual lines. Truly modern physics, I think, begins, however, with Maxwell in the mid-19th century. And the crown jewel of Maxwell's work is of Maxwell's equations. These are Maxwell's equations in three different forms. One aspect of their beauty is that you can look at them from very different perspectives and capture their content in different ways. There's the integral form, the differential form, and especially the geometric or pictorial form. These equations tell us how electric and magnetic fields interact with each other and with currents and charges, electric currents and charges. They could be summarized like this. The way Maxwell arrived at his equations was to put together everything that was known about electric and magnetic fields and charges and currents at that time and try to capture them in definite equations. So there was Gauss's law, which tells you how electric flux is generated by charge inside. A similar law for magnetic fields, supplemented by the idea that there are no magnetic charges, so the flux is always zero. Ampere's law, which was discovered by Ørsted, saying that currents generate magnetic fields, and Faraday's law that says that if you have changing magnetic fields, they generate circulation of the electric field. When Maxwell put those together, he discovered that there was a contradiction with the law of conservation of charge. But like Plato, he didn't give up. He asked himself if he could fix that contradiction, and the way he fixed the contradiction was adding this term, a sort of dual to Faraday's law that says that changing electric fields can produce magnetic fields. So those are Maxwell's equations. What makes them so special? Well, three things. They have wonderfully powerful consequences. They have wonderfully pretty consequences, and especially important for the later parts of this lecture, they introduce a new idea of beauty into physics, the symmetry of equations. So let me show you that. Very briefly, each of those. As I mentioned, Faraday already had the effect that changing magnetic fields can produce electric fields. Maxwell introduced the idea that changing electric fields can produce magnetic fields. And now there was the possibility of changing magnetic fields producing electric fields, which are changing, which produce magnetic fields, and they can move along in a self-reinforcing disturbance. Maxwell could calculate how fast such disturbances would move, and he calculated that they would move at the speed of light. So, being a very clever fellow and a bold one, this is what he looked like at the time. He wrote, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena." And that, of course, well, not of course, but to this day, is our best understanding of the nature of light. It is a disturbance in electric and magnetic fields. But there's more. Besides the disturbances that shift with frequencies and wavelengths that correspond to visible light, the light that was known at the time, there are additional solutions with faster oscillations of shorter wavelength or slower oscillations of longer wavelength. And these were in the equations, but had not yet been observed as any physical phenomenon in the world. So today, they have been across a very wide spectrum, and they are such ingredients of everyday life as radio, microwaves, infrared, ultraviolet, X-rays. Today we cook with them, among other things, and take pictures of our insides. So that's pretty powerful. Beauty of solutions. Well, to really show the beauty of solutions, I should solve the equations in some non-trivial circumstance, and that's interesting but not suitable for this presentation. But fortunately, since Maxwell's equations are about light, I can just show a picture to show how pretty the solutions are. So here is a picture and how rich the solutions are of these basic equations. This is a picture of the shadow of a razor's edge taken in pure light, which nowadays is quite practical with a laser. And you see, the geometric shadow would be this barely visible line here dividing light from darkness. But the reality is much more structured, has these bands, darkness within light, light within darkness, and all of it can be compared with and accurately maps onto solving those simple equations. And then the third idea, symmetry of equations. This is less obvious than the symmetry of objects. What do we mean when we say an equation or a set of equations has symmetry? Well, it's this rather Delphic telegraphic concept. We say something, a set of equations, or one equation or more, has symmetry when you can change it or change them without changing their content. It's related to the symmetry of objects, say, because the definition of the symmetry of an object is that you can make transformations on it that would change an arbitrary shaped object but doesn't change the symmetric object. For instance, an equilateral triangle is not changed by rotation through 120 degrees around its center, whereas an arbitrary triangle would be. So a very baby example of equations that have symmetry is the equation x equals y, a nice balanced equation. So in the colloquial sense, we would certainly say this is a symmetric equation. And it's symmetric under what change can you make on it that doesn't change it? Well, if you change x into y and y into x, sort of the simplest possible change you could imagine on these two quantities, then x equals y turns into a different equation, y equals x, but of course it has exactly the same content. And that's why this picks out the symmetric equations. X equals y plus 2 wouldn't work. It would change into y equals x plus 2, which is something different, and it's not symmetric. The symmetry of Maxwell's equations is not a baby symmetry. It's a much more subtle and consequential symmetry. And in fact, Maxwell didn't know about it. Maxwell didn't know about the symmetry of equations. As I mentioned, he discovered them by analysis of experimental data plus demanding intellectual consistency. But Lorentz and Poincaré explicitly looked for transformations of Maxwell's equations which didn't change their content. In the modern sense, they looked for the symmetry of Maxwell's equations. And in that way, they discovered the equations that later figured in Einstein's special theory of relativity. They had the equations, but not the physical interpretation of what those strange transformations that mix up space and time meant as physical transformations. But today, one way of formulating the special theory of relativity is it says that you can change the equations of Maxwell and, after modification, also Newtonian mechanics, in such a way that if you change to a system that's moving with constant velocity with respect to your original system, the equations all change, things look different, get shuffled around, but the content of the basic equations remains the same. There's also a less familiar form of symmetry that was extracted later in the 20th century from Maxwell's equations, and its meaning only became really clear when it appeared in quantum theory. That's gauge invariance. I won't have time to really do justice to that, but I'd like to state, without fear of contradiction, that this less familiar kind of symmetry has come to dominate fundamental physics in the latter part of the 20th century. And remarkably, it basically also goes the other way. Conversely, if you postulate these two symmetries and the general framework of quantum theory, then you are led with very few choices to Maxwell's equations as the simplest equations that embody these two kinds of symmetries. So it's a remarkable correspondence between the real and the ideal. Heinrich Hertz, the experimentalist who set out to prove the existence of these new forms of light that Maxwell predicted, and finally succeeded 25 years later after Maxwell wrote down the equations and had already passed away, said the following: one cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get out of them more than was originally put into them. And that, to me, is one of the definitions of beauty. You get more out than you put in. Okay, so now let's move to quantum proper, the quantum world proper, after those preparations. And the first quantum mechanical object I'll discuss is a guitar. Guitars, when you sound the different notes, vibrate in different ways. They set air into vibration. That's how they work. And you can take pictures where the bits of the guitar that don't vibrate, that the nodes of the standing waves, if you like, look black, and the vibrating parts reflect light better and are illuminated. And you see nice patterns associated with different notes, A, B, C, D. Actually, I don't think they're actually the notes A, B, C, D. But you can also have less musical, but more entrancing and regular mathematical patterns if you take vibrating plates, if you set them into vibration at different frequencies. If you do the right frequencies, they form simple patterns of nodes. And in this case, you can see the nodes by putting down sand grains on the plate and seeing where they accumulate. They accumulate at these black spots here, the nodes. And these are called Chladni figures, and you can see that they're very beautiful and regular standing waves associated with geometric objects. The remarkable thing is that the mathematics of standing waves, which is the mathematics of musical instruments, turns out also to be the mathematics of electrons and atoms. So that when people first started working with these equations, there weren't textbooks of quantum mechanics. They went back to Lord Rayleigh's theory of sound to learn how to solve these equations and work with them. In the case of atoms, we're not dealing with waves with disturbances in pressure and density, which is what sound waves are, but something more abstract. The waves describe real and imaginary parts of wave functions, and some of the squares of those is describing the electron probability. But leaving aside the technicalities of how you interpret the equations are basically the same equation. And the patterns here of electrons, of an electron, I should say, whose waves are standing waves subject to the influence of a proton around the middle, very much resemble, and it's no accident, the vibration patterns we saw of guitars and of plates. But this doesn't do it justice. Because it's a two-dimensional projection that just shows the probability. If you take a cutaway and look at phase in three-dimensional space of what these tones of the atom look like, you find marvelous geometric patterns. This is one of the stationary states of hydrogen, one of its pure vibration states, one of its tones. And you see it's a very marvelous, intricate object. And I should say, of course, this is pure Photoshop, plus Mathematica. One doesn't actually see these in the laboratory. However, the consequences of these equations have been checked out to 9 decimal places in some cases. So there's very little doubt that they have some bearing on reality. Whoops, sorry. There's a delay here that I'm having trouble mastering. But I really want to get the point. Try it one more time, then I won't, then I'll just tell you. No, okay, it's not going to work. Just to repeat, the mathematics of musical instruments is the mathematics, oh, there it goes, is the mathematics of standing waves. This is also the mathematics of electrons and atoms. I think if Pythagoras existed and he came back to this world today, he would be very pleased to see this kind of harmony underlies deep reality. That was carbon, that was hydrogen, the very simplest atom. This kind of beauty and capturing geometric structures and that emerge from simple equations and map onto reality permeates all of chemistry. It would take many lectures to do any kind of justice to that, but to delimit my subject and sort of make it as challenging as possible and yet succeed, I'll just concentrate on the chemistry of pure carbon, soot, dirt, sort of the most unpromising material you could imagine, and the simplest, just pure one element carbon. So in the case of hydrogen, there was just one attractive center for one electron, and we got these basically spherically symmetric kinds of configurations as the pure tones. In an environment where you have several centers, the electrons, instead of being concentrated around one, like to reach out and feel the attraction of several nuclei. And in particular, if you imagine carbon nuclei separated around, the electrons can reach from one to the nearest neighbor by occupying cigar-like orbitals. And that's the kind of thing that will minimize the energy and therefore will be realized in nature. Each carbon atom has 4 electrons to dispose of. There are 2 especially symmetric ways to arrange 4 cigars coming out of a center. One is that they can point to the vertices of one of Plato's regular solids, the tetrahedron. And that's what they do in one of the pure forms of carbon, namely diamond. Each carbon atom is surrounded by 3 cigar-like orbitals of electrons going to its neighbors. And they they point to the vertices of a regular tetrahedron. This is so symmetric and unique that it makes the electrons very happy. And that's why diamond is so hard. It's very difficult to persuade the electrons to do anything else. But another thing that can happen, that's slightly less symmetric, I'll have to say it, is that you can have 3 of the orbitals pointing to the vertices of a regular triangle, an equilateral triangle, and one pointing out into the orthogonal transverse direction. So the rule then is for planar objects that each carbon should be linked to 3 neighbors by cigar-like orbitals. And the simplest way to do that, the most regular symmetric way to do that, is to make this kind of honeycomb configuration. This is the substance called graphene, which was analyzed theoretically back in the 1940s, but only produced experimentally a few years ago, for which Gaiman of Ocelov won the Nobel Prize. So that is a beautiful, but I should emphasize that many of its properties were predicted in advance just from the equations without having the substance, because the equations could be solved, they're so symmetric, and proved to be reliable. One can roll up the graphene to make tubes. In fact, one can roll it up in various ways. These are called nanotubes. You can roll it up with different radii. Also, you can offset before you close it up, introducing twists and different sizes. The equations of quantum mechanics allow you to predict the properties of these materials. Some are electric conductors, some are electric insulators. The differences depend on very delicate details of how they're folded up. And one can check that that actually corresponds to reality, and even design new materials based on this kind of insight. So it's a marvelous match between ideal mathematics and physical reality. One can fold even further to make zero-dimensional objects, points if you like, namely molecules. Here is the famous buckyball, carbon-60. This was discovered experimentally, also not very long ago, and won the Nobel Prize for its discoverers. It was discovered in soot, literally. It's a main component of soot. It's, again, features this three-neighbor reaching out. Okay. It's not quite, it's an equilateral triangle, but bent a little bit so that the thing can fold into a solid. The mathematical rules say that if you want to have these three neighbored objects fold into a closed network, then what you need is to start with the dodecahedron, start with 12 pentagonal sides, and then you can fill in with an arbitrary number of hexagons. So this particular design turns out to be especially energetically favorable. It's also the one used in soccer balls. So evidently in chemistry, even the chemistry of pure carbon, but more generally, nature plays the theme and variations on the theme of symmetry. Now I'd like to pass to the current frontiers of physics, the quantum beauty of unification. So let me introduce that. I'm sorry. This shouldn't be happening, but somehow the presentation has got a life of its own. All right. Okay. This is our friend, the dodecahedron, a familiar object. It has 12 pentagonal sides, so it's very convenient for making a calendar. And you can find such things. And so if you went to the internet and saw this on some web page, you would know what it was meant to be immediately. Okay? It's got pentagons that need three at a corner, and has 12 of them, so it's obviously meant to be a dodecahedron that you should fold up. But suppose some evil influence erased some of it, and you were presented with this. Well, it might not be so obvious what this is meant to be, but then if you realize that there are only a few regular solids, there are only a few Platonic solids, only one of them, and they're very special, only one of them has pentagons, and the pentagons meet 3 on the side, you might guess that this is really meant to be a pentagon, but some evil influence, dodecahedron, but some evil influence has erased some of it. Okay, keep that in mind. And this is the standard model of particle physics. It would be difficult to exaggerate how powerful and accurate and compact and elegant this description of the basic laws of nature are. It summarizes basically everything we know about the fundamental interactions. People have spent, these equations kind of crystallized in the mid-1970s. Experimentalists ever since have been trying to knock them down. There would be glory in such a thing, prizes. But instead, they've only held up better and better to scrutiny. This rather cartoonish presentation is, however, completely honest. If you know the rules of symmetry and group theory and relativistic quantum physics, this is enough to reconstruct the main properties of all the particles involved. SU3, the group of the strong interactions, acts on a so-called color charge. They all obey versions of Maxwell's equations. Maxwell's equations on steroids. Instead of having one charge, you have 3 charges, or 2, or the 1 of the original Maxwell's equations. But that's it. And if you implement those symmetry-based equations, they turn out to describe the world. So this is pretty elegant. But since it is so close to nature's last word, we should have very high standards. And by the highest standards, it's not quite there. Instead of 1 force, which you'd like to have, we have 3. Plus gravity, which I haven't mentioned. That'll come in a little later. We have, instead of 1 fundamental material, okay, these different colors of quarks, or up and down quarks, for instance, are related by symmetries. So they're like the different sides of dodecahedron. If one exists, the other has to exist and has predictable properties. So really, anything that transforms into another thing should be considered as the same thing. And if we allow that, we need 6 building blocks of matter. And that's not very many in some sense, but it's still a lot more than 1. And then there are 2 repeats, which I won't say anything more about. And then there's the Higgs particle, which I also won't say much more about, unless asked. But this is the core of the standard model. So again, it's remarkably compact and elegant considering how much it covers, but not the end of the heart's desire. Can we do better? Well, the rules of symmetry, as we've seen, are very constraining of equations, just as they were very constraining of the shapes of Platonic solids. And so we can ask, are there larger versions of Maxwell's equations, larger symmetries that we might investigate, under which we'd have more transformations, and these would all come together, and of course these would be included as subsymmetries. So filling out the dodecahedron, if you like, with possible missing pieces. And of course, I wouldn't be telling you about all this if it didn't work. So here's how it works. And this is for experts, mathematicians. If you expand the symmetry to SO10, the group of orthogonal transformations in 10 dimensions, and look at the spinor representation, all the particles line up beautifully. There are different charges that under the subsymmetries that made it look lopsided can all now be derived from this structure if you erase appropriate parts. And instead of 3 forces and 6 materials in this more expanded, more symmetric description, we have just 1 material and just 1 force. So it's very tantalizing. But this is supposed to be physics, so we need to compare with reality. And if we do a reality check on this vision, we quickly seem to run into trouble. A prediction of the symmetry is that all the forces should have the same strength. They don't. In fact, the strong force really is the strongest. The so-called weak force, that SU2, if you measure at subnuclear distances, actually is weaker than the strong force, but stronger than electromagnetism. And electromagnetism's the weakest. I'll have to speed up now, which I will. But fortunately, we learn in studying the dynamics of the standard model that what we see is not quite what we get, that in a quantum theory, what appears to our ordinary senses as empty space is full of fluctuating, spontaneously fluctuating quantum fields. This is an actual picture of typical fluctuations in gluon fields of QCD. This is showing their energy density. The brightest spots are the most dense, then the less bright spots are less dense, and then at a certain point it's cut off so you can see. And this is going on all the time, everywhere, according to the principles of the standard model that have been checked very accurately experimentally. So this is what your eyes would see if they were nimble enough to resolve 10 to the minus 24 seconds and 10 to the minus 14th centimeters. So when we look at the basic interactions, we're actually seeing it through this kind of distorting medium. We have to make corrections if we want to see what the basic interactions are. We're like fish looking through water that sees distorted shapes. So we can do that with the stroke of a pen. So if we take the strong interaction and plot it in this particular way on a logarithmic scale in energy or inverse distance, and in terms of inverse coupling, the details are not important for this discussion, but if you do that properly, it turns out to look more or less like a straight line. We can do the same thing for the weak interaction and test the hypothesis that they actually unify, that they're actually at some shorter distance the same strength. And sure enough, it works. On the other hand, two lines do tend to meet in a point, so this is maybe not as impressive as it could be. There are actually several ways it could have gone wrong, but still, two lines do tend to meet in a point. So we have a third interaction, so we can test it. Here it comes. Dope. Not quite. Almost, not quite. So how do we react to this disaster? It almost works, but not quite. Well, beautiful ideas are precious. We shouldn't give up too easily, even though Popper tells us the goal of scientific theories is to produce falsifiable statements. And we've produced not only falsifiable, but actually false statements. We shouldn't be satisfied. We want to salvage these near misses that are based on beautiful ideas. So maybe we haven't been bold enough. Seems we've been pretty bold. We've unified, hypothetically, the description of electrons and quarks by having symmetry transformations that change one into the other. Also, we've unified the description of photons, the mediators of the electromagnetic force, and gluons, the mediators of the strong force. So we had one kind of material, one kind of force. You'll notice, however, that we still have two things. So the issue is, can we do this? That seems very difficult because it looks like apples and oranges. The behavior of electrons and photons is drastically different, even at any level. Electrons obey the Pauli exclusion principle. They don't like to be in the same quantum state. They're so-called fermions. Bosons love to be in the same quantum state. They make lasers. They're bosons. And to reconcile these, we need a new idea that was only invented in 1973, the idea of supersymmetry. Supersymmetry is a new kind of symmetry that gives us equations that we can make transformations on that change bosons into fermions and fermions into bosons, allow us to imagine unifying forces and materials by symmetry transformations that change one material into the other in the equations, but don't change the content of the equations overall. The way that works is to imagine a new quantum dimension of space-time. A quantum dimension is actually quite simple to describe what it is. An ordinary dimension is described by a real number. It tells you how far you move in that direction. A quantum dimension is described by numbers such that x times y equals minus y times x, so-called Grassmann numbers. And that's really the only difference. But a result of that is that x squared is 0. So quantum dimensions turn out to be very small. If you try to make 2 steps, you can't do it. And so it just has these 2 possibilities of bosons and fermions, but you can flip them. And in fact, if you expand the equations to have superspace and supersymmetry, it becomes very simple to flip and move around, and it's really fun, kind of addictive. And we can change the apples into the oranges. There's a lot to say about this, but I'm already a bit over time, so I'll make it short. Supersymmetry brings in new fluctuations, new kinds of virtual particles, new complications in what we perceive as empty space. And so we have to redo that calculation of the correction to our vision to see how things are really behaving at short distances. In addition to the gluons we knew about, there are gluinos and so forth, all of which are making further distortions. So what happens when we do that? Now they all come together. If you complete the structure so that it works also at high energies, once they come together, they stay together. And furthermore, a miracle, gravity, which starts out incredibly weaker than the other forces, not just a difference of a factor of 10, but 10 to the 40th. So way outside the known universe. This was very difficult to draw, also useless. But the last part, you can see gravity changes in a different way in response to higher energy, much more drastically than the other forces, and more or less unifies with them, which it had no a priori reason to do if these ideas are wrong. So if Susie's new particles are too heavy, the fluctuations aren't big enough and they can't do this job, so some of them should be accessible at the LHC. Now, in view of the time, I will just flash by a picture of the LHC. If you fly over Geneva and look down, you may see this big red ring. That's the LHC. It's 26 kilometers around. Inside, you see some very tired engineers who are responsible for making the magnets and the cryogenics and so forth work to contain these protons. Some very, very fancy detectors are necessary to figure out what's going on. So you see the scale of this, packed with state-of-the-art and beyond state-of-the-art electronics to track these very fast-moving particles, distinguish their tracks and one from another, and how energy is deposited, how they respond to magnetic fields, all kinds of things you need to do to reconstruct what happened in these little bangs that have fundamental information about the forces at high energy and short distances. This one is actually the CMS, where C stands for compact. This is the smaller of the 2 major detectors at the LHC. The Atlas detector is about twice as large in each dimension. So thanks to the efforts and investment of these people and governments, we will have a trial by fire. These new particles that required for supersymmetry and to culminate the vision of symmetry in the world that seems so logical and powerful in the development of physics, they better show up at the LHC. In this trial of by fire, they might all disappear, and the idea goes up in smoke. But alternatively, maybe when we analyze the collisions using these fancy detectors, sorting out this kind of thing, the vast majority of the time, it'll just reflect processes that are known from the standard model. But maybe once in a trillion times, you'll find some extra tracks that are something else. They have to be interpreted, and very elaborate computer programs model the standard model background and also what new physics would look like. And it's possible that after we decode the message, we'll find that what it's saying is, and then this vision of symmetry as a guide to new physics and the description of the world will reach a new level. So we've heard sirens sing. Here's a picture of it. There I am and the sirens. And we even know what they're singing. The forces unify. And another prediction of low energy supersymmetry was that the Higgs particle should be light, and that turns out to be correct also. So it's very tantalizing. And that's the question of the moment. So soon we'll learn whether nature has been subtle or malicious, and whether this use of beauty and symmetry as a guide to how nature works continues to go from triumph to triumph in the history of ideas. Okay, thank you.